So now for, this is only the fifth one. So we have a conducting loop in the shape of a rectangle, and it moves to the right. And we've got a B field. So we've got our conducting loop moving with some velocity. And we've got a B field going into the page. Of 0.06 Tesla. And so it asks, first of all, when the loop is still entirely within the region, what is the magnitude and direction of the current flow? So our EMF is minus derivative of the flux with time. Our flux is B dot A. So when it's completely within the, immersed in the region, then our area, which is given as 5 centimeters by 2 centimeters. So nothing's changing though. So our B dot A is just our B field times our area. And so then our flux, our EMF, is the minus the derivative of our B times our area with time. And so then it equals 0. And so our current, which is our EMF over our resistance, is equal to 0. So when it's fully immersed in the field, we have no current. And then, so for B, when it's moving out of the field, so now we've got our B field, and we're moving out of the field with velocity V. This is 2 centimeters. And now all that matters is the area that's within the field, which is going to be our full length minus our velocity times time. So then our area is 2 centimeters times our 5 centimeters minus our velocity times time, which is equal to 10 centimeters squared minus 2 centimeters times velocity time. So then our flux, which is our B field dotted with our area, is going to be B times 10 centimeters squared minus 2 centimeters times our velocity time. Our EMF, which is minus d phi by dt, is going to be the derivative of this expression with time. And as we can see, this part doesn't depend on time, so it's going to go to 0. And then the derivative of time here is going to leave us with B. The minuses will cancel, so B times 2 centimeters times velocity. And we can actually calculate our value now. So our EMF is going to be 0.06 Tesla. We can convert our 2 centimeters to meters, so 0.02 meters times our velocity, which is given in the question as 60 meters per second. And so 0.06, is that right? Oh, it's 0.06 Tesla. For some reason, I did all my calculations with 0.05, which... Okay, well, gives us So 12, and I'm just going to recalculate a bit, I guess. .072. So that's 0.72 volts. And so then the question says, the resistance of the wire is 5 ohms. So from Ohm's law, we have that our current is our EMF over our resistance. So 0.072 volts over our resistance, which is 5 ohms, which comes out to be 0.0144 amps. Okay. And so then there's our current. The direction of positive current will be clockwise around the loop. So that EMF will give us a clockwise positive current, which makes sense if we use our right-hand rule. Point our fingers in the direction of the current, at least on this loop here, and our palm facing the direction of the B field, and our thumb will point in the direction of the force. We know the direction of the force should oppose the change in flux, so should try to move it back into the B field. And so our net force is going to be to the left. So that makes sense. Okay. And so our EMF is 0.072 volts, and our current is 14.4, and the direction of positive current will be in the clockwise direction. So that looks good. So that's correct.